All right, we're back. We're on page 204. We're working our way through polar coordinates. We just found out that x is equal to r cosine theta, y is equal to r sine theta, r squared equals x squared plus y squared, and sometimes we have to use tangent of theta equals y over x. These are the big formulas that you're going to use all the time when you're converting these things. Let's convert some things that aren't points. So there's one highlighted point. I wanted to avoid saying a point. So there's one point that I want to make about converting points. A point stays a point. So a point in xy becomes a point in polar. So that seems like a stupid thing to say, but I've been doing this a long time, and I know that people mess that up all the time. I don't really know what the logic is that causes it to mess up, but if you're converting an xy ordered pair, you get an r theta ordered pair, like always. If you're converting something that has an equal sign, you'll get something that has an equal sign. So functions become functions, points become points. So let's do some problems. It's weird that I said functions become functions because the first one we're going to do is actually not a function, right? X equals -9 is not a function. So let's see if we can convert it though. So it's a certain logic that you just have to kind of get your head around. So x equals -9. So what does x equal in polar, right? So x equals -9. X is r times cosine of theta equals -9. Okay, so we don't want to stop there. In rectangular, y is a function of x. X is the independent, y is the dependent variable. In polar, r is the dependent and theta is the independent variable. So you want to write r as a function of theta. So what we want to do is we want to go from here to r equals -9 over cosine of theta, which is fine. And you could potentially stop there. We don't actually, whoa. We don't want to stop there though, right? Because that's awkward. So we're going to say r is -9. What's 1 over cosine? 1 over cosine is secant. So secant of theta. So x equals -9 becomes r equals -9 secant of theta. So you're going to find that x frequently goes with cosine things, y frequently goes with sine things, which makes sense because x is literally r times cosine and y is literally r times sine. So it makes sense that x goes with a cosine thing and y is going to go with a sine thing. But in this case, x is going with secant. Is there anything special about -9 though? Or could it have been any number at all? It could have been any number. It wouldn't have changed our work. So we're going to find that x equals k is going to become r equals k times secant of theta. I don't believe that that's worth memorizing, but it is a generalization that you can make, which may be the word that I was trying to think of in the last video, if you remember me stumbling around. Try to draw, I don't know. Honestly, I just don't know. I feel like I've forgotten a word, or maybe I didn't forget a word, and that's even weirder. It's like I invented a word that didn't exist and then I forgot it. Let's keep going. Y equals 12. Same process, basically. So y equals 12, but y is equal to r sine theta. So we get that. But then r is a function of theta, so we want to solve for r. So we get r is 12 over sine theta. But this is like just as awkward, right? So we don't want to leave this. So we're going to say that r equals 12 cosecant theta. So y equals a constant becomes a sine type thing, but not sine. It becomes 1 over sine. So here we got r equals 12 cosecant, but there was nothing special about 12. It could have been any number, probably any non-zero number. The origin is just r equals 0. Well, no, I guess that still would have worked. But if you have y equal to k, then that's always going to become r equals k times cosecant of theta. And again, I don't think it's worth memorizing that, but it's worth being aware of it so that you can interpret and anticipate is really what you want. All right, now let me take a second here. X equals -9 is about as good as an equation will get in rectangular, and then we converted it to polar and it became kind of terrible because secant has asymptotes all over the place, which brings up like, how are these the same? It's not really the time to talk about that yet, so I'm going to gloss over the issue, but it has to do with the fact that as theta, for example, in r equals negative 9 secant theta is theta varies between negative pi over 2 and pi over 2. R takes on every single value from negative infinity up to negative 9. And that's basically why this works out, but we'll talk more about that eventually. So don't worry about that now. But nice things in rectangular are becoming gross things in polar is kind of the point. So y equals 3x plus 5 is a very nice thing in rectangular, so it's probably not going to be that nice in polar. So let's do it. So first, y equals 3x plus 5. You can save yourself like half a step, but like only half a step. If you rearrange this first and say negative 3x, whoa, negative 3x plus y equals 5. You're not saving yourself anything meaningful, but like, you know, you save a step, you save a step. So r cosine theta is, what is that? X equals r cosine theta. And then y equals r sine theta. And then the whole thing equals 5. So we want to solve for r because r is the dependent variable, and you want to solve for the dependent variable. So I'm going to say, we can factor it out and get negative 3 cosine theta, and then plus sine theta equals 5. Ooh, more parentheses, equals 5. And then, so what I'm going to do is I'm going to just solve for r in this box. R equals 5 over. I'm going to start with sine because I would rather start with a positive thing. So I'm going to say sine minus 3 cosine. There you go. So a really nice rectangular thing became a not super nice polar thing. It's kind of a theme. Things that look nice in rectangular will look bad in polar. Things that look nice in polar will often look bad or at least worse in rectangular. So let's do this one. Same basic problem. So 2x plus y equals 8. So 2r cosine plus r sine equals 8. And then we can factor, ooh, look at that, and get r. And so I'm going to flip it again and say sine of theta plus 2 cosine of theta. If you're really interested, you can come up with a generalization for y equals mx plus b. I am here to tell you, it's not really that common to deal with y equals mx plus b, so it's definitely a waste of brain space. But you could do it if you, I don't know, if you're doing some kind of like coding thing or whatever, where this like keeps coming up, like go for it. Otherwise, it's questionable utility. Sine of theta plus 2 cosine of theta. Okay, so we've converted a bunch of lines. And then the next thing we want to do is convert a bunch of circles. So I'm going to convert this one, and then I think I will cut this video and come back and talk more about more things in a second. All right, x squared plus y squared. Well, think of the formulas we know. X is r cosine, y is r sine, tan of theta is y over x, and r squared equals x squared plus y squared. So we can actually replace this whole thing. I don't like that color. I'm about to highlight. Here we go. This whole thing is just going to be r squared. Now you get two options from this. So either r equals 3 or r equals negative 3. So typically what you do is you take the positive. So I'm just going to do that. I'm going to say r equals 3. Now what happens is they give you like slightly different graphing. They'll give you the same path. Like you'll end up with the same track drawn on your paper, but you go around the track in a slightly different way. So if you use r equals 3, where am I going to fit this? I'll do r equals 3 here. So this will be r equals 3. And it's going to be a circle of radius 3, which you already knew, right? Graph the rectangular one because you recognize it. You get this. You're here at theta equals 0. You're here at theta equals pi over 2. And you just keep going, right? If you choose r equals negative 3, I'm going to do it over here. So if I choose r equals negative 3, it's still just a circle that has a radius of 3. But when theta is 0, you're facing the positive x-axis, but you walk backwards. So you're actually here at theta equals 0. And then when theta equals pi over 2, r is negative 3. So you're like looking up, but you're going to go down. So here, your theta equals pi over 2. So it's weird. Like you're going in, you're not where you think you'll be when you think you'll be there, which is why we typically just use the r equals 3 version. But both of them exist. Both of them are options. Neither one is like wrong per se, but r equals 3 is like, it's like the principal circle, I guess you might say. All right, so what I'm going to do is I'm going to stop this here, come back in the next video, do a bunch more, and I will see you then.